Why is the universe 13.7 billion years old? Why is our solar system 4.5 billion years old? And not, say, 6 billion or 600 million years old? How is the age of the universe, as well as the Earth, the solar system, and the Milky Way galaxy, known? I'm sure many people have wondered about this question, which, by the way, has been of interest since ancient times. In fact, this question is one that only modern science has been able to answer. Until the second half of the 18th century, it was believed that the universe was eternal and unchanging. Later, it was thought that the creation of the world occurred in 3929 BC, based on an analysis of biblical texts. It wasn't until 1787 that French naturalist Georges Louis Leclerc concluded that if our planet had been a ball of molten iron at birth, it would take 75,000 to 168,000 years to cool down to its present temperature. In other words, he estimated the age of the Earth and the Sun based on physical models. 108 years later, Irish mathematician and engineer John Perry recalculated the thermal history of the Earth and determined its age at 2 to 3 billion years. At the very beginning of the 20th century, Lord Kelvin came to the conclusion that if the Sun gradually shrinks and shines solely by releasing gravitational energy, the age of our star, and, therefore, the maximum age of the Earth and other planets, could be several hundred million years. But at that time, geologists could neither confirm nor refute these estimates due to the lack of reliable methods of geochronology. In the middle of the first decade of the 20th century, Ernest Rutherford and American chemist Bertram Boltwood developed a framework for radiometric dating of terrestrial rocks, which showed that Perry was much closer to the truth. In the 1920s, mineral samples whose radiometric age approached 2 billion years were found. Later geologists have repeatedly raised this value, and by now it has more than doubled to 4.4 billion years. More data is provided by the study of celestial rocks, meteorites. Almost all radiometric estimates of their age fall within the interval of 4 to 4.6 billion years. Modern helioseismology makes it possible to directly determine the age of the Sun, which, according to the latest data, is 4.56 to 4.58 billion years. Since the duration of the gravitational condensation of the protosolar cloud was counted only in millions of years, we can confidently state that no more than 4.6 billion years have passed from the beginning of this process to our days. Solar matter contains many elements heavier than helium, which were formed in the thermonuclear furnaces of massive stars of previous generations, which burned out and exploded in supernovae. This means that the extent of the existence of the universe greatly exceeds the age of the solar system. In order to determine the measure of this success, it is necessary to go first to our galaxy and then beyond its limits. The lifetime of our galaxy can be determined in different ways, but we will limit ourselves to the two most reliable. The first method is based on monitoring the glow of white dwarfs. These compact and initially very hot celestial bodies represent the final stage in the life of almost all but the most massive stars. To become a white dwarf, a star must completely burn off all of its thermonuclear fuel and undergo several cataclysmic events, such as becoming a red giant for a while. A typical white dwarf is composed almost entirely of carbon and oxygen ions immersed in the degenerate electron gas and has a thin atmosphere dominated by hydrogen or helium. Its surface temperature ranges from 8,000 to 40,000 K, while the central zone is heated to millions or even tens of millions of degrees. According to theoretical models, there may be dwarfs composed mainly of oxygen, neon, and magnesium, which, under certain conditions, turn into stars with masses of 8 to 10.5 or even up to 12 solar masses. Still, their existence has not yet been proven. The theory also states that stars with at least twice the mass of the Sun end up as helium white dwarfs. Such stars are very numerous, but they burn hydrogen very slowly and therefore live many tens or hundreds of millions of years. Since a white dwarf cannot sustain fusion reactions, it shines due to stored energy and therefore cools down slowly. The rate of this cooling can be calculated and, on this basis, we can determine the time needed to decrease the surface temperature from the initial 1. For a typical dwarf this is about 150,000 K, to the observed 1. Since we are interested in the age of the galaxy, we should look for the longest lived, therefore also the coldest white dwarfs. Modern telescopes allow us to detect intragalactic dwarfs with a surface temperature of less than 4,000 K, whose luminosity is 30,000 times lower than that of the Sun. So far they haven't been found. Perhaps they don't exist at all, or there are very few of them. It follows that our galaxy can't be older than 15 billion years, otherwise they would be present in appreciable quantities. This is the upper limit of age. And what can be said about the lower one? The coldest currently known white dwarfs were recorded by the Hubble Space Telescope in 2002 and 2007. Calculations have shown that their age is 11.5 to 12 billion years. We must also add to this the age of the progenitor stars, from half a billion to a billion years. It follows that the Milky Way is by no means younger than 13 billion years. So the final estimate of its age, based on observations of white dwarfs, is about 13 to 15 billion years old. That is the first method. The second one is based on the study of globular star clusters located in the peripheral zone of the Milky Way and orbiting its nucleus. They contain from hundreds of thousands to more than a million stars, connected by mutual gravity. Globular clusters exist in almost all large galaxies, and their number sometimes reaches many thousands. New stars are practically never born there, but elderly luminaries are present in abundance. About 160 such globular clusters have been registered in our galaxy, and perhaps 2 or 3 dozen more will be discovered. The dating of the formation of the oldest globular clusters allows us to set the lower limit of the galactic age as well. It is very complicated technically, but it is based on a very simple idea. All cluster stars, from the supermassive to the lightest ones, are formed from the same gas cloud and are therefore born almost simultaneously. Over time, they burn out the main hydrogen reserves, some earlier, others later. At this stage, the star leaves the main sequence and undergoes a series of transformations, which culminate either in a complete gravitational collapse, followed by the formation of a neutron star or a black hole, or in the formation of a white dwarf. Therefore, the study of the composition of a globular cluster makes it possible to determine its age quite accurately. For reliable statistics, the number of clusters studied should be at least several dozen. Monitoring of 41 globular clusters in our galaxy showed that their average age is 12.8 billion years. However, our galaxy must be older than its clusters. Its first supermassive stars exploded supernovae and ejected into space the nuclei of many elements, in particular, the nuclei of the stable isotope beryllium. Beryllium-9. When globular clusters began to form, their newborn stars already contained beryllium, and the more of it the later they arose. By the beryllium content in their atmospheres, we can figure out how much younger the clusters are than the galaxy. As the data for the NGC 6937 cluster show, this difference is 200 to 300 million years old. Therefore, we can say that the age of the Milky Way exceeds 13 billion years and possibly reaches 13.3 to 13.4 billion years. This is almost the same estimate as that based on observations of white dwarfs, but it is obtained in a completely different way. But how was the age of the universe estimated? The scientific formulation of this question became possible only at the beginning of the second quarter of the last century. In the late 1920s, Edwin Hubble was engaged in refining the distances to dozens of nebulae outside the Milky Way, which only a few years earlier had come to be considered independent galaxies. These galaxies are moving away from the Sun at radial velocities, which have been measured by the redshift of their spectra. Although the distances to most of these galaxies could be determined with a large error, Hubble still found that they were roughly proportional to the radial velocities. 2 years later, he confirmed this conclusion based on observations of other galaxies. Some of them are more than 100 million light-years away. This data formed the basis of the famous formula, known as Hubble's law. Here v is the radial velocity of the galaxy in relation to the Earth, d is the distance, and h0 is the constant of proportionality. In 1927 Georges Lemaitre showed that the general theory of relativity allows us to interpret the movement of galaxies as evidence of the expansion of the universe. 4 years later he had the courage to take this deduction to its logical conclusion by hypothesizing that the universe arose from a virtually point-like embryo, which he, for lack of a better term, called an atom. This primordial atom could stay in a stable state for any time up to infinity. But its explosion gave birth to an expanding space filled with matter and radiation, which in a finite time gave rise to the present universe. Based on this work of Lemaitre and the later works of Hubble and other cosmologists, it was explicitly stated that the age of the universe, of course, counted from the initial moment of its expansion, depends on the value, which is now called Hubble time. The nature of this dependence is determined by a particular model of the universe. If we believe that we live in a flat universe filled with gravitational matter and radiation, then to calculate its age, Hubble time must be multiplied by 2/3. That's where the hitch occurred. From Hubble's measurements, it emerged that the universe was born 1.2 billion years ago, which clearly contradicted even the severely underestimated assessments of the age of the Earth at that time. It was possible to get out of this quandary by assuming that the galaxies were moving apart more slowly than Hubble had thought. Over time, this assumption was confirmed, but it didn't solve the problem. In general terms, this contradiction was resolved in 1998 to 1999, when two teams of astronomers proved that over the past 5 to 6 billion years, outer space has been expanding at an increasing rather than decreasing rate. This acceleration is usually explained by the fact that in our universe the influence of the anti-gravity factor, the so-called dark energy, the density of which doesn't change with time, is increasing. The duration of the existence of the universe with an anti-gravity component doesn't have to equate to 2/3 of Hubble time. Therefore, the discovery of the accelerating expansion of the universe, awarded the Nobel Prize in 2011, made it possible to eliminate the divergence between the cosmological and astronomical estimates of its lifetime. It was also a prelude to the development of a new method for dating its birth. On June 30, 2001, NASA sent the Explorer 80 probe into space. It was able to register the temperature fluctuations of microwave cosmic rays with an angular resolution of fewer than 0.3 of a degree. Fluctuations of relic radiation are generated by density variations of the electron-photon gas, which once filled the cosmic space. When this temperature fluctuation dropped to nearly zero, almost all the free electrons fused with the nuclei of hydrogen, helium, and lithium, thus giving rise to neutral atoms. Before that, sound waves were propagating in the electron-photon gas, which was influenced by the gravitational fields of dark matter particles. These waves imprinted on the spectrum of relic radiation, which can be deciphered using the theoretical apparatus of cosmology and magnetic hydrodynamics. As the latest calculations show, its most probable extent is 13.799 billion years. Thus, astronomers, estimating the age of the universe in 3 different ways, got quite compatible results. So now we know, or, to put it more cautiously, we think we know, when our universe emerged, at least within a few 100 million years. Who knows, perhaps someday our descendants will add the solution to this age-old riddle to the list of the most remarkable achievements of astronomy and astrophysics.